Okay, so for your lesson this week, your only lesson this week since I'm putting it up so late, we're going to do a quick review of just kind of basics of real numbers, and you'll need to know this stuff for algebra. We're going to use it once we get into the actual coursework. This is kind of pre-work that we're doing. All right, so we're going to start off talking about numbers. We can categorize any number into one of two categories. It's either a real number or an imaginary number, and that sounds really funny, right? Like, isn't a number a number? But imaginary numbers are things that aren't actually there. We can just talk about the idea of them in math, like the square root of -1. You can't really have a square root of a negative number. It's not possible. But in math, sometimes that comes up in higher level math, like calculus and trig and things like that. So in math, we refer to the answer to this as I. It's an imaginary number. So that's not what we're focused on now. I'm just telling you what that is. We're going to focus on kind of the easier ones, the real numbers. So for real numbers, all real numbers are either rational numbers, I'm going to write more next to this, or irrational. And if they're irrational, they stop right there, okay? And we'll get into that in a second. I'll write down what rational and irrational are. Okay, the next thing, actually, let's go back to this. Let's go to this center circle because we kind of build from there. In this center circle here under rational numbers, these are our natural numbers. Natural counting numbers just start with 1 and go up. If you can count them like on your fingers, or they can go up as far as you want, those are natural numbers. So it doesn't include 0, nothing negative, no decimals, nothing like that. Natural numbers are also grouped under rational numbers in the whole number category. So whole numbers are all natural numbers and also the number 0. So the only difference in whole numbers and natural numbers is that whole numbers also include the number 0. Some people say they remember that because the word whole has an O in it, so the whole numbers have a 0. The next category after whole numbers are integers. So integers are also like counting numbers, but they're negative numbers, 0, and positive numbers. So -3, -2, -1, 0, 1, and they keep going on from there infinitely, but just kind of showing you how it wraps. So all the counting negative numbers, 0, and all the positive counting numbers. And then all of those can be categorized as rational numbers. A rational number is any number that can be written as a ratio. So down here, any number that can be written as a ratio. And what's another word for ratio? A fraction. So any number that you can write as a fraction is a rational number. If you can't write it as a fraction, then it's irrational. So an irrational number are decimals that are either non-repeating or non-terminating. And I'll show you what that means. It's not as hard as it sounds. Non-repeating, non-terminating decimals are irrational numbers. So what are we oh, I didn't realize you could see that, sorry. I have my paper over. So what are we talking about? An example of a irrational number would be like 0.157266834 blah blah blah, and it keeps going on and on forever. So a non-terminating decimal never stops. It just keeps going. They're the kind of decimals that fill up your calculator screen, right? If the calculator was bigger, they'd keep going, but it's limited to the whole screen of the calculator. And also, none of these have a pattern. There's no repeating sections here. There's no pattern to this. So any yucky looking long decimal that's hard to know what to do with, that's an irrational number. You can have a decimal in rational numbers, like 0.3333333, right? That's repeating, so that's a rational number. Also, 0.2. It stops. There's nothing beyond the 2. It stops. That's a terminating decimal. That can also be written as a fraction or a ratio. So that's what these two are. They're all underneath the real number category. So let's kind of categorize or classify 3 numbers here for an example. All right, I got cut off. I got to apparently empty some stuff off my phone. I'm filming it on my phone. All right, so examples, 5 over 22. We're just gonna start with real or imaginary. It's not, you can go back up here and look at this to help you. It's not imaginary. None of the numbers we're gonna go over are imaginary, they're all real. So we know it's a real number. Then we go down to rational or irrational. Well, can it be written as a ratio? Yeah, that's exactly what it is. It's written as a ratio or a fraction. So we know it's rational. Is it anything else? Well, under the rational category, does it also fit into this? Well, it's 5 over 22. If I divided that, it'd be a decimal, right? All these other numbers up here underneath rational have no decimals in them. They're counting numbers, right? Either negative or positive counting numbers. No in between. So this is an in between number. It's less than 1. So it's nothing else. It's rational and we're done. Number 2, the square root of 81. So first we want to simplify that. What is the square root of 81? If you answered 9, good job. It's crooked. So the number 9, what does that fit in? What categories does that fit in up here? Rational or irrational or rational? We can write it as 9 over 1. So it's rational. Is it an integer? Is it one of the counting numbers, negative or positive? Yeah, it's 9. It fits over here. Is it a whole number? Yeah, whole numbers are 0 and up, counting numbers. Yep, 9 fits in here. And is it a natural number? 1 and up, counting numbers. Yep, absolutely. So it's everything. So we're going to write rational. All right, it's crooked. And then integers, whole numbers, and natural numbers. Integer. Oh, I said I'm on the wrong order. Natural. So the square root of 81 is rational, it's an integer, it's a whole number, and it's a natural number. And then lastly, the square root of 56. So you need your calculator for that to simplify it. If we look up the square root of 56, we get 0.748331477. And it keeps going on and on and on forever, right? It's one of those messy numbers. So does it repeat anywhere? I mean, these 3's repeat, but a repeating decimal has the same pattern over and over, the same exact way. So no, there's no repeating portion here. Does it stop? No, it keeps going on and on and on forever, right? It fills up your entire calculator. It's a big old messy number, it's irrational. And we're done. There's no other subcategory under irrational. Okay, next section here. How can I write a repeating decimal as a fraction? This is kind of a cool skill, and if you didn't learn this, you have this video to go back and watch as much as you need to. Okay, so I'm going to start by writing an example, and I'm going to use 0.777777, and just, it keeps going on and on forever, right? It's non-terminating. It repeats the 7 on and on forever. Okay, so first step I need to do is identify the repeating portion of my decimal. So I'm going to put identify repeating part. Okay, so here my repeating part is 0. Well, the repeating part isn't 0 point, but the 7 is what's being repeated over and over and over again. So I'm going to put that little line over the 7, and that's just telling me that's the part that's repeating. We're going to do more examples here in a second. Okay, so once we do that, the next step is to set that equal to n. Set equal to n. Why n? It doesn't matter. It's just equal to a letter. Traditionally in math, though, for this lesson, we always use the letter n just to stay consistent. So we're going to set 0.7 equal to n. Now, that's a super important step that we're going to come back to, so don't forget that we did that. We're going to use it again in just a second. Okay, next thing we need to do is multiply to get anything that's repeating, this repeating portion. Here we just have a 7. We need to get the whole entire repeating portion in front of the decimal. Okay, so that's our next step. So we want to multiply to get repeat part in front of decimal. Okay, so here, how do I get 0.7? Just the set, it repeats on and on forever. It keeps going, but the portion that's being repeated is just the 7. So how do I just get that 7 here? How do I move that decimal place one space back? Can I just multiply by 10? right? And that would just multiply that back, okay, one place. So if I'm going to multiply this side by 10, I have to do the same thing over here. So I'm going to multiply this by 10n, or n by 10. So I get 10n, and then once I move that decimal place back one, I get 7.77777, right? Because all these sevens keep repeating. The sky's doing something weird, and it's casting an awful shadow, sorry. So I still have the rest of this repeating stuff, but I've just moved part of it in front of the decimal. The number you're going to have in front of n is always going to be a multiple of 10. So it might be 10, 100, 1,000. You'll kind of see it gets easier. Okay, so now we're going to go back to this part up here, right? After we've put the repeating part in front of the decimal, we want to get rid of that repeating part. So how the heck do I do that? I'm going to do the example first and then put it in words. How do I get rid of 0.7777777, right? How do I get rid of it? I'm just going to subtract it. And I know that the 0.7 repeating part, the repeating part here of my decimal, is equal to n. So I'm going to subtract n from one side of the equal sign. And then I'm going to subtract exactly what n is equal to. I can't subtract n from here because there are no other n's. But n is the same thing as 0.7 repeating. So I'm going to subtract 0.7 repeating over here. It's kind of a weird step, but you'll get used to it. So all I'm doing is subtracting the repeating part. I don't have a decimal over here, so I'm going to subtract what the decimal is equal to here. So 10n minus n is 9n. And then 7 point blah, 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 minus the whole blah, 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 blah. That part cancels. So I'm just left with 7. Cool, right? So when I write that step, I'm just going to write subtract n from both sides. And by both sides, I mean both sides of my equal sign. So I'm subtracting n. That gets rid of my repeating decimal part. And now I want to isolate n. So I'm going to put over here in the steps, solve for n. Solve for, oh gosh. You know how it feels like after summer when you haven't written a long time and then you're like, what is this handwriting I'm even using? It's weird, right? You have to warm up. Okay, so I'm going to divide this side by 9. Divide this side by 9. Get rid of those 9s. And I'm left with n equals 7 over 9. And if you actually went back in your calculator and did 7 divided by 9, guess what you'd get? 0.7 repeating. So those are the steps. We're going to do a few examples here and then move on. I only have one other page of notes, so I'm almost finished. I know it sounds like I'm blabbering on. Okay, so for number 1 here, first step is to identify the repeating part. So it looks like this 314 keeps getting repeated. 314, 314, 314, 314. So my repeating part is 0.314, and I'm going to put that line over the whole thing, and I'm going to set it equal to n. Those are my first 2 steps. Okay, then I need to get the repeated part in front of the decimal. So what do I need to multiply it by to move that decimal back 1 space, 2 space, 3 spaces? If I wanted to move back 1 space, I'd multiply by 10. Multiply it by 100 to move it 2 spaces. So I'd have to multiply it by 1,000 to move it 3 spaces. So I'm going to multiply both sides of my equal sign by 1,000. And that's going to move that 314 in front of the decimal, but it still repeats after that, right? It keeps on going forever. Okay, so now I'm here. Next step is to subtract n from both sides. So I'm going to subtract n from here. I'm going to subtract just my repeating decimal part here, because after all, that's what it's equal to in this step up top. So those cancel, and I'm left with just 314 on one side of my equal sign, and then 1,000n minus n gives me 999n. All right, and then the last step is to get n alone, so I'm going to divide by 999 on both sides of my equal sign. N equals 314 over 999. And sometimes you can even simplify that fraction down. I'm not worried about that part. If you got this far and you're right, that's good enough for me. So if you went in your calculator and you divided 314 by 999, you would get 0.314. Okay, 2 more. While I'm solving these 2, by the way, for all my videos, you guys can pause the video at any time. If I'm talking too much or you're trying to catch up or whatever, just pause it. Go back and watch it again. That's the bonus part of having videos taped. Okay, so here, first step, n equals my repeated part. It looks like it's saying 6, 1, 6, 1, 6, 1. So the repeated part is just 6, 1. So I put the line over it. Then I've got to multiply to get the repeated part in front of the decimal. I've got to move it 2 decimal places. So I'm going to multiply it by 100. However many decimal places you're moving it, that's how many zeros you need here. So I'm moving it 2 times, so I need 2 zeros here. 100n equals 61. And then I still have that repeating part there. It keeps going on. Then I subtract in. I subtract my repeated part. I'm left with 99n equals, this thing cancels, so just 61. And then the last step is to divide by 99. So n equals 61 over 99. And maybe that simplifies more, maybe it doesn't. I don't care. Just leave it right there. You're good to go. All right, and then finally, number 3, last example for this. This is a big one. We have 0.3724, 3724, 3724, dot, dot, dot. So the repeating part is actually 4 numbers. 3724. That's the piece that keeps going on forever. So we're going to have to multiply by a big number. We need 1, 2, 3, 4 zeros. So 1, 2, 3, 4 zeros. That's 10,000 times n equals, and then all of that repeating part moves in front of the decimal. 3724. And then it's still there behind the decimal. It keeps on repeating. 0.3724 repeating. Then I subtract n from one side, and I subtract what n is equal to from the other side, 0.3724 repeating. So this repeating part gets canceled out, and I'm left with 10,000n minus 1n gives me 9999n equals 3724, and I just canceled out the repeating part. Oops, sorry. Then I divide everything by 9999, 9999, and that's what n equals. N equals this big old number, and we're done. And you can always go back and check by taking out your calculator, 3724 divided by 9999, and you'll get this big old long repeating decimal. Kind of cool, right? I mean, as far as math goes, kind of neat to know how to do that. Okay, next page of notes. Rules for radicals. Hope you guys remember what you do with radicals, right? Like radical sign is like a square root sign. So we're going to go over those real quick. Just do a couple examples and move on. All right, so first thing, number 1, when you separate factors underneath a radical symbol, you can rewrite each factor under its own radical symbol and multiply them together. What did I just say? All right, so if I had square root of 36, right? I'm going to separate that. Factors of 36 are like 6 and 6, 9 and 4, 2 and 18, right? There's a bunch of different ones. So I'm going to separate it into 9 times 4. Same thing. 36 is the same thing as 9 times 4. This is under the radical. This is under the radical. Well, this just said whenever I multiply numbers under the radical, I can actually give each of those numbers its own radical symbol. So this is the same thing as saying square root of 9 times the square root of 4. This and this are the same thing. So now, can I simplify those? Yeah, because both of these are perfect squares, right? They have an exact perfect, you can take the square root of it without any decimals or anything. So the square root of 9 is 3, the square root of 4 is 2, and 3 times 2 is 6. So that's a cool little rule. We also just know that the square root of 36 is 6. That's just a funny way of getting to it. All right, number 2, a radical symbol is the opposite of an exponent. All right, so if I had 7 and I square it, that's an exponent, right? That equals 49. If I were to undo that or do the opposite, I could say radical over 49, the square root of 49 equals 7, right? This exponent and this radical symbol, they kind of undo each other. They're opposites. So basically, that just tells us that the square root of 7 squared is just 7. this little squared symbol and this square root symbol cancel each other out. Easy peasy, right? Number 3, when a fraction is under a radical sign, you can rewrite the numerator under its own radical and the denominator under its own radical. Okay, so if I had the square root of, 25 over 49. I can separate this big old square root symbol into the top and the bottom of the fraction. So that's the same as saying square root of 25 over square root of 49. And then I can simplify from there, right? So square root of 25 is 5. Square root of 49 is 7. Easy enough. Let's do another one. Square root of 9 over 81. Now you could obviously separate your fraction, or you could simplify your fraction here. You can do that. That's fine. That's not what I want to do in this example, but you could. All right, so I'm going to separate my radical. Excuse me. Oh, got a tickle. All right, and the square root of 9 is 3. And the square root of 81 is 9. And then can I simplify that fraction? Yes, I can. I can divide the top and the bottom by 3. 3 divided by 3 is 1. 9 divided by 3 is 3. And then the last step here is never, ever, ever, ever leave a radical sign on the bottom of a fraction. Never do it. You always have to cancel it out, simplify it further. If you leave it on the bottom, it's just wrong. You just can't do it. It's just not simplified all the way. So, for example, if I gave you 4 over 5 underneath a radical, find the square root of 4/5. I can separate that, square root of 4 over square root of 5, and I can simplify it. Square root of 4 is 2, right? But I can't find the square root of 5. I mean, I could. It'd be a nasty decimal. I don't want to estimate it around the decimal. I want to keep it that exact number. So I have to just keep it under the radical, right? So I'm done. No, I'm not. You cannot leave a radical symbol here. Okay, so how do I get rid of it then? Hopefully you guys remember this from your last class. If you didn't learn it, no problem. You can go back and watch this or ask me more questions. But we just talked about up here in number 2 that the exponents and radical signs cancel each other out. So what's going to cancel out a square root symbol? A squared symbol, right? So I need to square this whole term to give it a little 2 somehow, and then that little 2 will cancel out with this radical. So how do I do that? Can I just square the top and the bottom? Well, no, because then that changes the value of my fraction. I have to keep the fraction this same value. So basically I need to multiply it by 1. Right? So I have to multiply it by 1, and I also have to get this to be squared. So what's a way I could do that? I'm going to multiply it by the denominator over the denominator, right? A number over itself is just 1. So when I multiply this fraction by this, I'm not changing the value anywhere. And then also, once I multiply it across, 2 times square root of 5 over, this becomes square root of 5 times square root of 5, which is square root of 5 squared. And that's exactly what I want, right? Now this little squared symbol is going to cancel out this square root symbol, and I'm left with just a 5. So I get 2 square root of 5 over 5. Done. Now I don't have a radical on the bottom. Top, that's fine. You can have a radical sign on top of a fraction all day long. You just can't leave it on the bottom. So that's a way to do it. Whatever your denominator is, multiply the top and the bottom by that guy. And that means you're squaring the bottom and you're getting rid of that radical symbol. Ask me about that if that was confusing. All right, last little portion of this is adding. All right, so when we're adding and subtracting negative, positive numbers, and 0, right? Counting numbers, no decimals, no fractions, just regular old numbers. If both of the numbers, if the numbers, when we add them together, if 2 signs are touching and they're the same, you're always going to add. So for example, if I had 4 plus positive 3, right? That's an obvious one. We're still going to add. If I had 7 minus negative 2, I'll put parentheses there. Those 2 signs are touching each other. There's no numbers in between them, and they're the same sign. So that's going to be 7 plus 2, which is 9. You're always going to add when your signs are the same. So if they're plus plus or minus minus, you're always going to add. All right, and then if the signs are different, if signs that are touching, doesn't matter what each of the numbers are, it's just the signs that are touching. If the signs that are touching are different, you're always going to subtract. Always. Okay, so if I had 7 plus negative 6, right? These two signs are touching. There's no numbers between them. Yes, I know there's a parentheses, but there's no numbers between them. If the two signs here are different, you're going to subtract. So this is the same as saying 7 minus 6, which would be 1. Okay, also if I had, I don't know, 2 plus negative 8. Same thing, the signs are different. Or I could say 2 minus positive 8. Same thing, right? We would subtract here. So I'd say 2 minus 8, which is negative 6. There is no rule about what your answer ends up being when you're adding or subtracting. That can be whatever. It just depends on what the numbers are. The rule is where the signs are touching. Where the signs are touching, if there's two signs touching, we got to change it to just one sign touching. How do we know what sign to change it to? Well, if the touching signs are the same, we add. And if the touching signs are different, we subtract. We change it to a minus sign. All right, and then the additive inverse is a rule that we have, and we're using it in algebra actually a lot. So the additive inverse just says if you add opposite numbers, when you add opposite numbers, like for example, 6 plus, and then the opposite of positive 6 is negative 6. When you add opposite numbers, the answer is always 0. And that's what our additive inverse says. So inverse numbers, when we're talking about additive inverse, just have opposite signs in front of them. They're the same number, but they have opposite signs. So for example, we could say negative 7 plus 7. That would be 0. We could say 8 plus negative 8. That would be 0. Another way we can write it, and it gets a little confusing, is when you see the same sign numbers being subtracted, right? And that's the same thing as the additive inverse. Okay, so these are special examples. This would be like if you saw 4 minus 4. We can actually rewrite this as 4 plus negative 4. It's the same thing, right? Like up here, I could have plus and negative, it changes to a minus. So I have plus and negative and it changes to a minus. When you see the same number being subtracted, that's the same thing as the additive inverse. They've just gone ahead and simplified it already. So the answer is still 0. 4 minus 4 is 0. 4 plus negative 4 is 0. So always assume for the additive inverse, when you see opposite numbers, you're adding them and you're always going to get 0. If I had 11 minus 11, that's like saying 11 plus negative 11, which again is 0. All right, and then lastly we have multiplication. So when we're multiplying numbers, if both numbers have the same sign, so they're both positive or they're both negative, the answer is always going to be positive. So we're going to put positive answer. If the two numbers that we're multiplying together have opposite signs, then the answer is always going to be negative answer. So for example, if I multiplied 4 times 3, they're both positive numbers, so my answer is going to be positive. If I multiplied negative 4 times negative 3, they both have the same sign, so my answer is positive. If I multiplied negative 4 times positive 3, they have opposite signs. One's negative, one's positive. So my answer is negative. And same if I did 4 times negative 3. Okay, so that's what the rule is saying. And we did additive inverse. That's when we add numbers with opposite signs. Multiplicative inverse sounds like the same thing, right? Like you would multiply 2 times negative 2. It's actually not, right? The signs make sense to us up here when we're talking about the additive inverse because we're talking about adding. Well, down here, we're not talking about adding, so plus signs aren't as important to us. Multiplicative inverse, or people say multiplication inverse, is just when you multiply a fraction or rational number, same thing, by its inverse. In other words, its reciprocal. Remember that number, that vocab word? When you multiply a fraction or a rational number by its reciprocal, you always get 1. The answer is 1. Multiply a fraction by its inverse, the answer is always 1. So for example, if I multiplied 2/3 times and I flip it upside down and make it 3/2, the answer is 1, right? 2 times 3 is 6, 3 times 2 is 6, so it's 1. If I have a negative, I keep the negative in my problem, right? If I had -5/3, I'm just flipping the two numbers. I'm taking the 3, putting it on top, the -5, putting it on bottom, so I'd have 3/-5. -5 times 3 is -15. 3 times -5 is -15, so the answer is 1. So multiplicative inverse, multiply reciprocals, answer is always 1. You guys are going to have an assignment that you need to fill out. I'll give you till Monday to finish that, no problem. It's just an assignment. It's not a quiz or anything, and I'm just going to count it as participation. But normally during the week, at the end of the week, I'll give you one of these, and I will grade it on how many you got right. But for this week, because it's the first week and I'm so late getting this up, it'll just be on whether you did it or not. So try it, play around with it, see how many of these you can get right, and as long as you finish it, you'll get 100 on that, okay? Let me know if you have questions.